Today we are starting with Stefan Leutenegger from TUM University, from the Technical University at Munich. Stefan is working with mobile robots, and he is going with his robots where no robot has gone before. And he is exploring unknown areas, environments, and so yeah. It sounds not that good as I was thinking about it, but it's some kind of Star Trekky now. Okay, anyway, so we have luckily Stefan will present us 2 talks this morning. So be prepared and have fun. So.
Okay, so I will present this talk in kind of 2 parts. The first one will be a little bit basic, going into theory, with the hope that then in the second part you'll understand a little bit more. But I'm also slightly embarrassed because there's a lot of professors and also very experienced PhD students in here. So maybe some of it is a bit repetition for some of you, but hopefully not all of it. So these are the sort of application areas that I work in, that I'm interested in, and that we are working on in my group. So that's what Jörn, I guess, meant with places where no robot has gone before. Maybe a bit of an exaggeration, for instance, for the vacuum cleaner, but I guess they have all in common that somehow they need some sort of localization and mapping and 3D perception. And maybe just a real example that we built already a few years ago, just as an introductory example a little bit. This was for a competition. Pedro was there as well, I just learned. So we built this kind of off-the-shelf robot and equipped it with some sensors and processors. So there's an Intel NUC on here, there's an RGBD and inertial sensor in the front. And so that's the one. And this is kind of like a cheap off-the-shelf hardware otherwise. There's also a downward-looking camera. Now the goal with a downward-looking camera was to try and find this moving vehicle and then actually land on it. So we did this outdoors, and actually without any GPS. We wanted this to work always, also indoors in any environment. And then we couple it. We use some visual inertial SLAM system, and we couple it with model predictive control. We have detected now this moving target. Yeah, some people had to run quite a bit on this day, and then it approaches it and lands on it. So it's actually quite classical stuff, right? Probabilistic SLAM, model predictive control, but it's not so easy to actually get it done. It has to work in all kinds of conditions. You have different wind, you have different illumination. This was still back in London, so sometimes you would even have some sun, and it has to be able to cope with that. So so this is just to give you a bit of an example of the kind of things that you have to do. This was fully autonomous, right? So we had, for the competition, you were only allowed to press one button, and then the rest had to be completely autonomous. So I like to show this map always a little bit in terms of what it means to do mobile robotics, because I think there's sort of 2 axes here that are important that determine, I think, the feasibility of some of these applications. What I've just shown is over here as something that somewhat worked, greenish, where I think, in some sense the task was relatively narrowly specified, right? We knew that we had to go and find this moving vehicle and land on it. It's kind of predetermined, really quite specific task. The other axis here is the environment. I mean, here we had some constraints in the environment. For instance, we assumed it was going to be flat and we didn't have to do any obstacle avoidance and so on. So some things were specified, but at the same time, I already mentioned, right, it had to cope in all kind of weather, in any kind of place, and we also wanted to even have this work indoors. So it's maybe somewhat in the middle. Now, when you look at other examples, for instance, a lawnmower robot is maybe a bit higher up here. Has to go into a bit different environment. Still quite clearly specified task. The stuff that really works well, assembly robots, maybe not even mobile ones, right? They sit somewhat down here. Really very controlled environments, very narrowly specified tasks, maybe just pre-programmed. So this is the kind of stuff that really works without a doubt. Now, if we're going towards the upper right corner here, this is really, I think, where things don't work. This is where we want to go, but this is also super hard. So some kind of general household help robot. I mean, we've seen brilliant examples yesterday, but they were perhaps not in completely open-ended environments, right? So that's still the frontier that we have still in robotics. I think that these kind of things start to actually work once you have a somewhat controlled, still specific environment. But if you just place it into any kind of environment that the robot hasn't seen before, we are not quite there yet. So I want you to keep this in mind, perhaps with the rest of the things that I'll be talking about. Now, also the way that we are actually approaching this in robotics traditionally has been a somewhat modular architecture, and also think that probably what we've seen yesterday, it very much follows such kind of architectures, that you have some sort of perception here, then maybe you have some estimation, and you kind of feed this forward, and you have some cognition, path planning, and ultimately you come up with a motion control, and you act, and the whole thing repeats. This is a sort of real-time control loop typically. And at the same time, this actually allows us to introspect. It's easy to understand what's going on. We really know what we're doing here. Also for a user, if you have an operator, you can actually see what's going on. You can look at these kind of things, maps and coordinates and so on. But I would argue that there are certain problems, that there's always kind of gaps happening here between the sort of sensing side and maybe the AI side on the right here, that sometimes things go wrong, we misinterpret stuff, and you know, autonomous cars crash and things happen. So of course in that sense it's not surprising that the more end-to-end kind of say deep reinforcement learning kind of ideas are very appealing, because you got rid of these sort of bottlenecks, right? You don't have to explicitly specify these interfaces. You're not going to make mistakes by assuming certain interfaces and so on. You just say that all of the representations in here, all the signals, is kind of self-learned, and it should kind of just work by itself. Now that's of course in that sense very appealing, but I would also argue that at the same time you lose the guarantees. It's kind of difficult to introspect what's going on. And I think maybe the main one here is down here. So these things work really well, and I will also argue for actually using these sorts of things. It works really well for sort of well-defined tasks. Things like locomotion, things like just grasping something, for instance, has shown really, I think, remarkable progress. But if you want to do something more complex, then I would argue a sort of end-to-end learning black box approach like this is not going to be data efficient enough to train anything that is somewhat more complex, right? Some real-world interaction, elder care. How are you going to train this? You're also going to have difficulties simulating everything, right? So I think here is really the data efficiency ultimately what's going to hinder these kind of very radical new approaches. So I think, you know, the community is somewhat converging towards leveraging the benefits of learning, but still keeping some structure, some modularity, such that you can still train individual blocks, and you don't have to be as data efficient, because you don't have to train this kind of gigantic neural networks, as we have seen them very successful in other places like large language models. Okay. So that's maybe a little bit the background. Now I will be mostly talking about SLAM and what I call spatial AI here. So let's just look at the very basic kind of SLAM problem. I mean, I'll talk about this in a little bit more detail. You assume there is some kind of a 3D structure in the world, some kind of a map, say there's a couple of key points. Now you're observing them by a camera from different viewpoints. Say you have it here first, and you move the camera, and you re-observe it, and you hope that you can now find the pose of this camera, of both cameras, the relative pose, as well as the 3D landmarks here. Now this is vision only, and a thing that I will also be briefly talking about is that it really works well if you're trying to combine different sensors inspired by humans. What we are doing is we're not just using a single camera, right? We have also several sensors. We have perhaps stereo vision here, and then in our inner ear we can sense accelerations, we can sense rotation rates, we combine all of this, and then we come up with some sort of an idea of how we are moving. I have no idea how this works here, right? I can only say that the way that we are trying to replicate this thing is very similar. So we can use stereo cameras, we can use inertial measurement units, and we can use coded maths to basically come up with the same here. Okay, so this was maybe with a focus on just motion tracking, but I would like to see the whole kind of estimation stack as something like a bit of a pyramid, where at the very basic, yeah, you have things like visual inertial localization and mapping, where it's really all about motion. That allows you to do position control, for instance, for a drone. But then you really want to do more. You want to have some kind of a richer, dense environment understanding that allows you to do some motion planning, collision avoidance. And then you might want really a semantic layer. You might want to understand this is the floor, that's the bed, and that allows you to do some more advanced task planning and even human-robot interaction. And ultimately, maybe this is more at the frontier of what we can do at the moment. You can even go towards object level maps. You can go towards maps that are changing, that are dynamically changing all the time, where maybe also people are part of it, actually. It's like a really much more general kind of understanding of the environment that includes the positioning of the robot and these individual objects. Okay, so with that, what can we now actually do? If we're approaching the whole robotic problem a bit more from the control side of things, you might be, looking at the system like this, where you have the robot dynamics sitting somewhat in the middle with inputs and robot states, internal states. Then you put the feedback controller around it. You're measuring some kind of thing here, and you can feed that back, and you have a control system. And you might say, okay, so this is how we do control in robotics as well. This is how we can get the mobile robot to drive around. Now the problem is a bit, and that's relating to what I said before, that now our measurements here, they are not directly something we can use for control, right? This might be an image and inertial measurements. So if you directly feed that back, it's really non-trivial controller, and then you're in some sort of, say, maybe deep learning territory that tries to map these sensors, sensor measurements to something that tries to control a robot. That's not intuitively clear. So what we are now trying actually to do is we're trying to have the state estimator here, right, to reconstruct something that we understand here, positions, orientations, and so on. And then this is something that we can feed back here. Okay, so that's the general idea, and then of course we can also add all kinds of planning in front of this here. Good. I guess some of this is of course repetition for many of you, so also feel free to ask questions if something isn't clear. Okay, so planning is perhaps all about finding trajectories that are safe, that do what we want. Control is all about finding the commands that get the robot to do the stuff that we want it to do. And then what I will always argue is that it's actually a good idea to leverage the understanding of the robot dynamics in this process of trying to control it, perhaps also in the process of finding trajectories here. At the same time here, the estimation is all about the best explanations for the states given the measurements. And also here, it's very important that we actually understand the process of how these measurements are generated, I will argue. This helps us finding good estimators here. Okay, so with this is now the plan for today. In the first part, all a bit these kind of basics on representations, sensors, estimation, and then the kind of pyramid of spatial AI from sparse visual inertial SLAM to dense semantics and object level maps. Afterwards, I will show some examples, also including then how they're used to control robots, especially drones, in the part 2. Okay, so let's get into it. Just maybe to start, there are a few things that are hard in robotics, I think, and they're surprisingly hard, and one of them is coordinates and transformations, and so I'm just going to introduce this here a little bit. About the notation that I'm using also. So what you typically have is you have several sensors that are somehow mounted on a robot, right? And then you have maybe a world frame sitting somewhere, and you can formulate now different relations in here. So what I'll be using is the left-hand index here that's actually saying in which frame the position here is represented. So the W would be in the world frame. And then yeah, we have also different frames here. So we have the inertial measurement unit, and this would be the S, and then we have the frame W, as I mentioned already. We have rotation matrices that can do the transformations of a vector, right? And for instance, we can use velocity vectors that are now expressed in different frames and so on. Okay, so this is just a bit of notation of what I'm using. And with this, you can now have, for instance, a state vector, a real-world state vector. This is actually from the example I've shown in the beginning, where you have now the position of the robot, you have the orientation of the robot here using a quaternion, you have the velocity, and then a couple of other things. So actually, it's very typical that we have some things that we really need to control the robot. So we have things like position, orientation, we might have velocity here as well. And then there's some stuff that we just need to estimate in order to be accurate, but we're not really interested in so much. So for instance, here this is an online calibration problem where we also have the relative poses of the camera, say, relative to the inertial measurement unit here. And then what we also have is some biases of the inertial measurement unit for the gyroscope and for the accelerometers. Now this is just an example, right? But I think it tells us that often we have some kind of physical robot states we are interested in for control, and then we have maybe some extrinsics. This doesn't work so well. We have some extrinsics here, sensor extrinsics, and some sensor intrinsics that we might have. Now, what exactly this looks like, it's up to us, right? We have to decide what is the application, what do we really need, how do we want to formulate this in order to make progress. And similarly, at the side of the map, maybe even more pronounced, is there's a lot of choice. How do we want to represent the environment? And here's just a couple of examples, right? We can work with sort of more 2.5D representations of depth maps. We can use with fully 3D volumetric maps. We can work with meshes. We can work with all kinds of point clouds or semi-dense kind of point clouds. So again, it's just a bit of a reminder that we have to choose what really are the right representations to achieve the task that we want to achieve. Also in terms of sensors, we have to kind of choose what are the right sensors to achieve the task that we want. We have outward-looking sensors, we have things like laser scanners, we have things like cameras, we have even magnetometers, pressure sensors, and then we have the more sort of inward-looking sensors. I mean, I put GPS here, it's maybe debatable if this is inward-looking, but it directly gives you the position. And if you can get that, if you're doing some robotics outside, I will argue you should use it. There's no point in not using it. But it sometimes doesn't work, and sometimes not available. We have encoders, we have inertial measurement units, right? So these are the more inward-looking sensors that we can use. Maybe important, the IMUs, these MEMS IMUs that we get, they actually measure rotation rates and accelerations. They don't measure orientations. If you get orientation out of it, it's already some kind of an estimate that has been computed. So what are the models now for these kind of sensors? A lot of times we have models like this, right? This is now for the IMU, say for the rotation rates, for instance, where you have some kind of you have here the true physical quantity, and then you have all kinds of nuisances. You might have some sort of a misalignment and scale that is multiplied in here to then generate the sensor measurement set. You might have some constant bias. You might have also, unfortunately, often some moving biases that are changing over time. And then you might have some noise, some time uncorrelated noise here, and of course some unmodeled effects. So this is the kind of typical model that we'll be using for these sorts of sensors. Now the camera is maybe a bit more specific, and again, I don't want to bore you. I know a lot of you. So who has already calibrated cameras and worked with camera models? Okay, so well, probably almost all of you. So just to go through this very quickly. So the physical process is perhaps also quite complicated, right? But we use a simplified model with the image plane in front of the camera, and then we have this kind of projection here onto the image plane. And a bit maybe more specifically, the typical model that we use is in 3D, we project onto the image plane a normalized unit kind of image plane in front of the camera. So this is just simply dividing by the set component here. And then we are applying some kind of a distortion model to compensate these unmodeled effects, which is just a mapping in the 2D plane. It's a sort of, heuristic really of something that people came up with a lot of parameters. And then in the end, we are applying some kind of scaling and centering of the pixel coordinates to the top left corner of the camera as a final step. So this is the kind of model that we'll be using, and we have, of course, all of these parameters that we have to sort of know. Okay, so with this, we are now equipped in terms of knowing how we can represent states, how we can represent environment. We know how the sensors work. We have mathematical models. There are, of course, always simplifications, but we have a forward process and importantly also probabilistic processes of how these things work. So now we can go into trying to reconstruct the state in an ideally probabilistic manner. So here's the idea. So we have these variables to be estimated. Let's call them x. We have measurements, say zi, that are actually assumed to be independent. So this is still a vector, so you can still have correlated subsets of these measurements, but the individual index I here are uncorrelated. And you have now some probabilistic measurement likelihood, right? So this is exactly the kind of model that I was talking about before. And maybe you will also have even some prior distribution for x, p of x. So now what I said is try to find the most likely explanation for these measurements. So this is really mathematically speaking just trying to find the argmax of the posterior distribution here, p of x given z. Now, what we can do to get p of x given z is we can basically apply Bayes' theorem, and we'll find that p of x given z is proportional to p of z given x. And that, in turn, because they are independent measurements, right, is just simply a big product of all of these measurement likelihoods. Okay. Maybe a bit more intuitively, in actually a maximum a posteriori estimation, you get p of x given z being proportional to p of z given x times the prior p of x. So this is kind of maybe a bit more directly the application of Bayes' theorem. So it's very similar, right? You have just one additional factor here, which is the prior. So now we're trying to find the argmax of this thing, and this is now leading us into batch estimation theory, right? So what we're doing here is we're using all of the measurements, and we're getting some kind of an estimate of all of the states, because, well, that's just kind of what we do here. We factored the whole distribution of everything. Now, with the assumption that these are normal distributed measurement likelihoods, it's a big assumption, right? But we assume that a lot, and with some, we have to at least know what we're doing. But if we are assuming that, then something nice happens. Well, first of all, we find here now this kind of nonlinear model that we have derived, for instance, in the camera projection. Right, so this is going to give our mean, and then we have just some covariance matrix here for the normal distribution that we have to know as well. Maybe we have also a Gaussian prior here, but something very nice happens that if we try to find the argmax of this p of x given z, we can equivalently find the argmin of the negative logarithm of this posterior distribution. And if we plug in all the stuff from before, something very nice happens. You might think, why would you take the negative logarithm instead of just the p of x directly? But actually, now because you have the logarithm of a big product, as I wrote it before, you turn this into ultimately a sum. Okay, so if we're just simply plugging in now the measurement likelihoods and the prior as normal distributions, you really just can write out the function of the normal distribution. You have this big exponential here, right? That they consist of. An exponential of is effectively the measurement minus your model of what the measurement should be, right? And this exponent here now, this product of this big exponent of these exponentials will simply now become a minimization effectively now of a sum of these kind of squares. So that's very nice, right? Because now we have a least squares problem, and we know that this least squares problem actually corresponds to probabilistic argmax that we are trying to find here, right? Where we have nicely, and this is maybe somewhat intuitive, we have nicely just weighted every one of the measurements with the inverse covariance matrix. So if we are very certain about something, right, then the matrix here will be very small, and therefore the inverse will be very big. So you get a high weight for something that you're certain about. Also, very nicely, this works out with the units here, right? The covariance matrix is always going to be in the units of the measurements that you have. So you take the inverse, so all of this is unit free, so you can now mix all kinds of measurements. It just automatically falls out all of this probabilistic estimation, right? So you can have GPS measurements mixed with inertial measurements, mixed with pixel kind of projections and so on. And you just have to know the covariances. And again, remember that this is assuming we have Gaussian distributions. So this is maximum likelihood, and if we do maximum a posteriori, the only difference was there was this additional factor, which was the prior, and this becomes now an additional part in the sum here that is also containing the prior. So it's basically very, very similar. All right. So this just to show you the probabilistic interpretation of what we do a lot with least squares minimization. Now, of course, the question is still how do we solve this? In the linear case, if we have a linear mapping here from the state X to our measurement domain, then we can directly find the solution via the normal equations, right? Linear least squares, you have a direct solution. What we're trying to do in the nonlinear case, we have a kind of cost landscape that's now not exactly quadratic, so we're trying to iteratively somehow with a starting guess find the minimum, right? And the way that we can do that is we can use linearization. So we can formulate these error terms that appear in this the least squares problem, right? So measurement minus your model h of x. We can denote that as an e, and we can simply use linearization now. So the idea is that we approximate this nonlinear function as using the Taylor expansion here. So we have the Jacobian matrix E evaluated at some x bar. So you start with an initial guess. You evaluate the Jacobian matrix at this initial guess, right? And with that, actually, then you can just, again, formulate the normal equations. You solve the normal equations having used the Jacobian here, okay? And you can compute with that an increment on the state, and basically, you solve for it, you apply it, and then you iterate the whole thing. So this is the Gauss-Newton method that falls out very naturally with this idea here of having now nonlinear measurement functions that we just simply linearize. And with that, once we have, say, a linear problem, we know we can just solve the normal equations. So that's a general idea of how we can solve these kind of problems. Of course, you have to check for convergence and then iterate this thing. So now kind of going back a bit to the problems that we try to solve in robotics, we typically can now distinguish localization problems where we are trying to find the argmax of only the position of the robot or the pose of the robot given the map. So here xm is the map. So here we assume that the map is given, and we have also given, of course, our measurements, and maybe also what is u here. Maybe this is controls, maybe this is odometry measurements, right? So here we're only trying to solve for the state of the robot. And now there are recursive and batch formulations of this. So in the recursive one, we are only trying to solve for the current robot state, and in the batch one for the entire trajectory of where the robot was. So that's localization, right? Important to know localization. We assume the map is given, is static, and is somehow given to us. In SLAM now, however, we are trying to solve for both the robot state and the map, okay? And again, here there's recursive and batch formulations. In the recursive formulation, you're only trying to find the current robot state. You're not interested in all the past robot states. So far, we've only talked about batch estimation, really. In mapping, it's kind of like the complement to localization, right? So you're trying to find what the map is given the robot states. Okay. So now here actually the model, the odometry or you know the controls don't really matter anymore. We have just given robot poses that matter, and then you measure somehow something about the map, and you can insert that into the problem. Okay. So also what I want to say is that a lot of practical approaches now kind of mix some of these things. Ideally, we always want to do SLAM if we don't know the map. Well, sometimes we do know the map though, right? And what we can also do is we can mix these things. We can, for instance, do a step of localization and then a step of mapping and alternate these, or we can use a SLAM system and then a mapping backend. So we have now this kind of ability to mix and match these things. And so now maybe a bit more mathematically than before, if we're now just doing this idea that I presented, this probabilistic estimation with key point projections, what comes out is the well-known bundle adjustment. So you have given somehow 2D measurements, 2D detections of 3D landmarks in the real world across different cameras. And you're trying to find what is the positions and orientations of the cameras, as well as what is the 3D locations of these landmarks. Okay, so that's the idea. And basically what we're trying to do is now minimize reprojection error, well, in a least square sense, as we just said before, right? So this is giving us then the kind of probabilistic estimator. Okay, so we have here the key point measurements minus what is the projection of the landmarks. The only thing you need to do is you need to first transform the landmarks that are represented in some kind of a world frame. You have to transform them into the respective camera frame, right? So in this TCIW here that does this transform, here you have the position and the rotation representation that you're trying to find. So that's why every reprojection error here is a function of the position of that respective camera where the landmark is observed, the orientation of the camera where this landmark is observed, and the position of the camera. So it's a function of these three quantities. And now you can just simply sum the squares of all of these things across all of the cameras and across all of the landmarks. So I'm not going into the details of how this now actually works. There's, of course, very nice libraries that do that, but maybe just one thing to mention is that this left-hand matrix that you get when formulating the normal equations turns out to be very sparse. So this is the sparsity pattern of what here Wikipedia says is a moderately sized bundle adjustment problem. And it basically it says that what you see here in what is the off-diagonal part is it basically just encodes now which landmark is observable where, in which part or in which image, right? So that's why you have here a sort of maybe strange sparsity pattern. Everything white here is 0, right? So this is a very special structure, and we can of course solve it efficiently with things like sparse Cholesky decomposition, or also using Schur complement operation to actually eliminate the landmarks first and then solve the remaining problem, which is much smaller. So there's a lot of tricks to solve this efficiently, and this being also part of the success story of why these things work well. Okay, so far now I have talked about measurements like that are happening in the image, but we haven't talked much about temporal models. We haven't talked much about how things are correlated over time, and I wanted to just briefly talk about that next. So here's an example of what you can do, taking into account also dynamics, just to show also a bit of examples here. So here we're flying around a drone, and we have actually identified the nonlinear dynamics of that drone quite well. This is something you can actually do quite well, and then you can apply model predictive control that exploits the knowledge of the dynamics, and it runs this forward simulation on board to try and find the optimal control for it to follow the trajectory that you want it to follow. And the nice thing about this kind of stuff is it really works in all kinds of unseen also states, right? So it's not like a learning problem where you have to make sure you have really learned all possible states and events, and it will just work. The other thing you can do using the model, and that's an estimation problem, is you can try and find how the model maybe matches or doesn't with what you observe. So here, for instance, we disabled a rotor and didn't tell the drone, and then the drone compares the temporal model to what it observes in terms of attitude and altitude here, and it can actually figure out that a motor must have stopped, and it can save it, right? So then the controller can be adapted accordingly. You just tell the controller, okay, your motor doesn't work anymore, and automatically, because you have this fully physics-based nonlinear model, it can save the drone and it will still work. So here we, again, importantly, we don't tell the controller that we have turned off. It has to find out before it crashes, and it does, and then it can continue to fly, right? So these kind of dynamical models are incredibly useful, I find, in estimation and control. So let's briefly talk about that. Also, just to show it doesn't only work once. Here you can see we did. This is actually 16, I think, successive experiments that we did where it didn't crash. So you can always do a paper with one experiment where things work, right? 16 in a row is a bit harder. Okay, good. So the kind of temporal models that we are using, they're often coming from physics, which live in this kind of continuous time world. So we formulate them in continuous time. They're often, unfortunately, also nonlinear models. So you have here the time derivative of your state, which is a function of your state, inputs u, and then maybe there's also some noise involved here, w. And then maybe also considering some nonlinear measurements already here. What we can always do is we can linearize them, stay in the continuous domain, or, and this is what we will be doing most, is to go into the discrete time world by integrating from a time step tk minus 1 to tk, and then we get a discrete time model here, right? This is still a nonlinear discrete time model using numerical integration. We can get that. So it's still nonlinear, but we can also use linearizations thereof for various things. Also, I want to distinguish kinematics versus dynamics. In kinematics, there are also temporal models, same as dynamic model, but you're actually only analyzing motion and not considering causes. So you're doing things like transformations and derivatives of transformations, velocities. In dynamics, we're actually going into really the causes. We're looking at forces, we're looking at torques, and how things, rigid bodies, react to them using Newton's second law. Okay. And now we can start to use these things in estimation and control. So for instance, we can look at I-mu kinematics. So if we just, this is really actually directly following out from maths here. We can build this kinematic model. Say the time derivative of the position is just simply the velocity. The time derivative of the orientation now here becomes a little bit more complicated. We can use quaternions here, for instance. But what we can see, and I'm not explaining all the details, right? But what we can see is that the time derivative of the quaternion is something that's somehow proportional to what is the rotation speed that you're measuring here with the I-mu. Now, unfortunately, we also have biases that we have to compensate. So this would be the true kind of rotation speed. So we have to compensate with biases, and we have to also account for noise that is entering the system here. And this is now, unfortunately, though, somewhat nonlinear, right? Velocity, that's maybe a bit easier again. So if we take the time derivative of the velocity, we get something like acceleration, right? Now the acceleration in the IMU will be measured in the inertial measurements coordinate frame, so we have to transform it back into the world frame if you want to have the velocity here in world frame. So here is also some nonlinearity, right? We have to do the transformation here, and this is where also the rotation, the orientation quaternion is basically part of this rotation matrix, right? And also here with the acceleration, we have to compensate for the bias here, we have to deduct the bias, and we have to account for noise that is entering the system. So this is a probabilistic, stochastic process, really. We have to also take into account gravity. So the accelerometers, they will also measure gravity. It's not the true acceleration in that sense. So we have to compensate for it here, for it to be the true acceleration. And then we have a model here for how the biases change over time. Now here we just used a random walk, Brownian motion. This is now somewhat our choice of how we model that. But unfortunately, it is just a fact that these biases are unfortunately, they are not static. So they will be moving around over time. Okay, so this is something that we can use now to formulate estimators and control as well. If we're talking about dynamics, of course you're all familiar with Newton's second law in one dimension, right? And you can simply write out the equations of motion for that. Now, unfortunately, it's going to be a little bit more difficult if we have general rigid bodies, but the idea is still the very same. All we have to do is we have to kind of find all the forces and torques that are acting on these bodies, and then Newton's second law formulated for rigid bodies will tell us the equations of motion, really, right? So not deriving them here, that's of course, again, it's somewhat non-linear, unfortunately. But the things that we have to do if we want to actually use these models, they're reduced to finding the forces and the torque. So this could be, for instance, on a drone, could be the individual thrusts that you have from the propellers and the weight force, and then you have to know the inertia and the mass that you have to plug in here, right? So these are the kind of things that you can now do with this. So this will be also models that we use. Okay, so how does this all help us in estimation? Well, now we can actually do this thing that is recursive estimation. For recursive estimation, you need a temporal model. So you can actually say we have a starting state here of a robot, for instance. So you have a sort of distribution for where the robot is. This is a two-wheel kind of robot, a diff drive robot in this example, just a 2D estimation problem. So you assume there is some sort of a probability distribution of where this robot is, and now you can actually take, say, wheel odometry measurements, or you can use your dynamical model with Newton's second law that you formulated and apply it, and you can find the new distribution of where the robot is now at the new time instance. And the idea is now that you're making some kind of a measurement to reduce the uncertainty again, right? So with the uncertain temporal model, with the probabilistic temporal model, your uncertainty will always be growing, and now you're making measurements to shrink it again. So for instance, it could be distance measurements here, right? And it has shrunk. Now the problem is that, of course, nobody ever knows the true distribution. There's no such thing. So what we will be doing is we'll approximate it. And you probably have done things like particle filters, so that's one way of doing it, approximating this distribution with a discrete set of particles. Or, and that's what I'll be mostly talking about, we can actually just, again, approximate these distributions with normal distributions. You might say, why would you ever do such a thing of using normal distributions when you can do more accurate things with particles? So maybe the question here, just to also check whether it's too hard or too easy what I'm saying. Why would you do one thing or the other? Yeah.
Normal distributions boils down to using the algebra, so it's very fast.
Say again, didn't quite hear the acoustic.
Normal distributions on calculating using the algebra, so it's very fast.
It is fast on computers, right? So if that's so fast, why are people using particle distributions then? Sometimes.
you can just increase accuracy by buying more power and increasing the number of particles.
Yes, yes. So this is right what you're saying. Just to be a bit more specific, maybe someone has something to add to that. I mean, it's entirely correct what you're saying. I mean, and maybe you say, well, if that's true, if I just need more power, then I'll just buy a bigger computer. We have big computers now, and I'll only ever do particle filters, and that's it. I'm done. Yeah?
You might have to sample particles
From a?
You have to put particles in the whole market.
Yes, yes. So it has to do also, I think you're getting into this direction. You want to repeat it, or? Yeah, so you might have a huge space from which to sample particles in principle, especially also an initial state that is unknown. And maybe even worse, you have what is called the curse of dimensionality, right? So in 2D, you might get away with particles. However, if you're doing things like estimating a bigger state where things are correlated, you have orientation in full 3D, and you have the 3D position as well, then at one point it becomes untractable to work with sufficiently many particles, and you can do still things very efficiently, assuming normal distributions. So the maths, as you were saying, becomes actually very efficient to do that. So there's no one answer. So sometimes one thing actually works, and sometimes the other. So you have to analyze what's feasible. Okay, so the way we are doing this is that basically now we can factorize the probability distribution in this way, that we have a starting state here, and then we have the next state, which is now dependent on our odometry measurement or our model and controls, and then we are making a measurement Z here, and the whole thing repeats. And we can actually write down this whole joint distribution of all of this with the starting distribution, and then the temporal model here, state transition model, and then here we have the measurement likelihood. So this gives us the distribution of all of these things, right? But what we now try to do in recursive estimation is to actually only get the current state, right? So we have to marginalize out other things. And this is now exactly what we will be doing. Instead of trying to now find the argmax in this distribution, we would be back in batch estimation theory. So now, however, we are trying to actually marginalize out stuff. So the way this now works is that in practice, you can alternate a step of prediction where you take your previous distribution, right? You are now applying the temporal model. So this is a step here that you just simply plug in your temporal model. So this is the previous distribution that you had, and then you plug in your temporal model. But now you have actually the distribution of your previous state and your current state, and you're not interested in the previous state anymore. So you're applying marginalization here. You're integrating out the previous state, and that's then your prediction. And in the update, this is simply an application of Bayes' theorem. Right. So you're multiplying here the measurement likelihood, and it's kind of a similar idea as what we have seen before. So with that, this actually is very nice. This gives you directly now also the particle filter equations, and it gives you also directly the EKF equations. In an extended Kalman filter, we are assuming that there are Gaussian distributions everywhere, and also, unfortunately, because we don't typically have linear models, linear state transition models and linear measurements, we have to apply linearization. So that's the kind of hack that we do. So we have this discrete time state transition model that we can now apply, where it is our odometry controls and where there is some noise entering the system, as we've seen before. And with that, we can propagate mean and covariance. So for the mean, we just plug it into the equations. For the covariance, we use linearized state transition here. And then we do the measurement update. And, again, I'm not deriving the equations here, but basically what you're computing is a bunch of stuff with matrices. This is just a recipe. And what you will be doing, again, is this kind of idea that you've seen before, that we're formulating this residual, where you have the measurement here, right, that is compared to the model. So we have our nonlinear measurement model here, where we plug in the current state estimate, and we can do the difference between the measurement that we have seen and the model. And this gives us an update in the end. Okay, so with that now, just a few examples of how this can actually be applied now to the kind of problems that we want. So this is now an example of such an estimator, visual inertial estimator actually. So you'll always have to still find these kind of 2D key point measurements that you have. This is now in a past keyframe. You have to find the matches, and then you can run such an estimator here that actually is trying to find the trajectory of the drone here, as well as the 3D landmarks. Right, so this is a visual inertial system, and it's kind of running a windowed batch estimator that can do this thing. So I'm slightly shortening this. So this first part of the landmarks is actually not so easy, right? So you have to find, first of all, you have to find the same landmarks across, or the same key points across the different images. So you have to have an algorithm here that gives you somewhat the same locations if you give it a different input image. And also, you have to then find a sort of matching algorithm, say a descriptor matching algorithm, that tells you which one is which, that should be reliably able to distinguish which one matches where. Another thing that in practice you will want to do is you might get drift as you're going around the loop, right? And so you might have a place recognition module that finds, oh, now I'm actually here, instead of what I thought previously would be here. So you might want to apply so-called loop closure that then tries to optimize here the whole trajectory again, trying to minimize the deviation of the relative poses that you had here around the loop. Okay. Now, I've talked for a long time, and I have a few slides left, but maybe let's include this into the part 2, because